Now, how much computing power do you need? I think this is like the biggest question, and I would like to come straight to the point. Now, see, if you have to do the aerodynamic analysis correctly, meaning upstream of 5 times the size of the car and 10 times the size of the car downstream, you need large machines. You need at least a minimum of 64 GB of RAM and 6 to 12 core machine so that you can run large jobs. You need a decent graphics card as well if you plan on making visualizations. Now, this is like the bare minimum configuration. Anything lower than that is not going to work. So say you have 32 GB RAM, that might sound like a lot when you're a student, but usually with this type of setup, you can run your computational mesh count would be around maybe up to 15 million maximum. That is, it changes with the CFD software that you're using, but 15 million is something that you can shoot for. And you need at least that much amount of cell so that you can at least predict the trend. You see what I'm saying? Meaning, say that you have 5 designs, right? The absolute drag force numbers cannot be comparable. I mean, if you actually take your car to a wind tunnel and you test out the 5 different designs, say that you get a particular value for the forces, you might not get the same thing in your simulation, but the trend will be the same. Meaning, say that I make a plot. I have design 1, design 2, design 3, design 4, and 5. And I'm plotting drag. I'm plotting drag force. So in my simulation, it could be that design 1 was really at a low drag, design 2 high drag, something like this. So if I create a chart, it's going to be like this. Now, when you do the experiments for the same thing, then it's pretty good if you actually get something like your absolute drag force doesn't matter, because let us say that this is your baseline design. Then you know that this design number 1 and 3 are good, because even in your experiment, design number 1 and 3 are better. The actual value doesn't matter. In fact, what people do is, with years and years of experience, you know that, okay, if my answers are off by this much, then I know that I can kind of shift it by applying a scaling factor. Meaning, for example, from here to here, the distance is always the same, right? The distance is the same. Again, I've drawn it like that, so it makes it convenient for me. So if I take my experimental data set and minus this distance, then I'm going to have both of the plots on the same, like they're going to be on top of each other. So this is what you need to shoot for. This is what you call as predicting the trend and not predicting the absolute values. And at this point, one thing that I would like to say is, many people that send me simulation results, they run it on a machine which has 4 GB RAM. And I immediately tell them that your results are wrong. And this is why I do that, right? Because there is no way you will get the right answer. Unless your velocity is like maybe half a meter per second, where it's almost laminar flow conditions. In that case, you don't have to do a CFD analysis at all.